Okay, guys, I'm sorry I can't be with you today. I'll try and go through this fairly quickly and then you can take notes from the PowerPoint. We did this before, so hopefully you remember doing it and there's worksheet to do. So stoichiometry, write down the learning intention, mass to mass stoichiometry, using the mass of one chemical in a reaction to find the mass of another via mole ratio. So we're going to use mole ratios a lot, and this one is just a mass to mass stoichiometry. So if you download the PowerPoint, then you probably need to take notes from the slides which have a green background, and the rest of it I'll kind of just be talking through. And I'll try and do it fairly quickly because I always go on and on and on. Alright, so stoichiometry comes from a Greek word, apparently meaning element, and metry is measuring. So it's the study basically of we're normally using ratios to find the amount of one substance given the amount of a different substance, and it's based on the conservation of mass, basically that you don't lose anything. Chemistry is kind of like cooking, really, in that you put certain things together in a certain ratio and then you make products in a certain ratio. So if you double the recipe, if I have 4 cups of flour, then I'm going to have to double everything else. I'll have to get 4 eggs, and then I'd double that and I'd make 30 pancakes. Or if I halved it, if I had 1 cup of flour, then I'd have to halve everything else. So I'd have 1 egg. And chemistry is the same. So these combinations, 2 cups to 2 eggs, it's a ratio, a 2 to 2 ratio. So the amount in a recipe it could be in mils or grams or cups. The recipe can be scaled up or down, but the ratio 2 to 2 or however many you've got stays the same. When we compare reactants to each other or to the products in chemistry, we have to compare them as moles. If given the amount in other units, so if you're told that you've got a certain mass of something or a concentration and volume of something, then you have to turn that into moles. So far we've looked at 4 equations. So you could pause this and have a little think. What are the 4 equations? So we've looked at finding the number of moles given a mass, finding the number of moles given the number of particles, and finding the number of moles given the concentration and volume, which is what you've just done. And this one, our ratio. So what do you want? What have you got? And how do they go together? So equivalent fractions, basically. So pause it again. You're going to have to be quick because I want to get through this. If you want to pause it and have a think. 7 types of reactions that we've looked at so far. The other class forgot all about the dissolving reactions. So combustion, addition with double bonds. Polymerization we didn't do an awful lot of. We did it fairly quickly, making plastics. So with lots of double bonds, one after another. We've been looking at these dissolving reactions. So dissociation, when you've got ionic compounds. Polar molecules can just dissolve as a whole polar molecule, or if they're an acid, they can lose their hydrogens and ionize. And then we've done our precipitation, whole and ionic. So all of these things we can do stoichiometry with. Ratios, any relationship between molecules, atoms, or ions will be the same whether they are individual atoms or if we scale it up and we have a whole mole. So anything that makes sense, if I'm talking about individual things, any amounts that we're talking about, we can scale up and those numbers will still be the same. So moles are just a group, they've got the same number of particles and the ideas are just scaled up. So combustion, we've done combustion reactions. I asked the other class what this was called. 1 carbon, so it's meth, and it's saturated, so it's a methane. When we combust it, react it with oxygen. For every one of these, we're going to need 2 of those. So by one, I mean 1 molecule, and we'll need 2 molecules. So these numbers at the front are a ratio. I need 1 of these for every 2 of those, or I need twice the number of this for every whatever that is. So if I've got 2 here, if I've doubled it, I will have to double this. If I've got 10 molecules, so 10 times that, I would have to have 10 times this. If I've got 100, I'd have to have 100 times. So 100 of these, I'd have to have 100 times that. I'd have to have 200. If I've got 100 of these, I would make 100 of those. So if I've got 6.02 by 10 to the 23 of these, I would need 6.02 by 10 to the 23 times this as well. So I'd need 12.04 by 10 to the 23, twice the amount. So what I'm talking about is if I had a mole. So if I scale it up so much that I've got a mole, however much I've got of that, I'd have to have twice the same, so 2 moles. So people, they're okay if I'm generally talking about individual molecules, but as soon as you scale it up to a mole, they lose the plot. But it's the same idea, just numbers of things. And instead of talking about huge numbers, we just collect it and talk about a group. So it's a 1 to 2 to 1 to 2 relationship. Okay. So the ratio is the same, and we can scale it up. And the numbers at the front connect all the particles for this particular recipe. So if we had a different recipe, I would need a different number of oxygen. You only use this number at the front when you're referring to something else. They go together based on the numbers at the front. If you're looking, quite often people want to use this number when they're working out the molar mass of oxygen or the molar mass of, of water. They'll try and go multiply it by 2. Water molecule is a water molecule, and you use the molar mass of the water molecule. You only use this number 2 when you're going, okay, I need, for every 2 of those, I'll only have 1 of those. So you only need the numbers at the front when you're going from one chemical to another. And they are a ratio. Alright, so we've done a combustion reaction example. Now we do our precipitation where we're making solid and we've got solutions. This is our ionic version. People weren't so great with writing the ionic version, so we're good with the whole ones but not so good with the ionic ones. So we can talk about this as individual ions, like molecules, individual ions. So 2 ions, 3 ions will get together to make 1 unit. I started off with the molecule example because that's one whole thing. We can't talk about, salts or lattices. This is one little collection with 2 aluminiums and 3 carbonates. So if I scaled this up, so I had 6.02 by 10 to the 23 times that, I'd get 2 moles. If I scaled this up, so I had 6.02 by 10 to the 23 times, I'd have 3 moles. So it's a 2 moles to 3 moles to 1 mole unit. So it's 2 to 3 to 1 ratio. So to prove that these are only useful for a particular recipe, for a particular reaction, I've got aluminium on the next one and it's reacting with phosphate. And instead of a 2 to 3, it's a 1 to 1. Okay? So different ratios to different recipes. All right, so pause it here and write this down. These are the steps I'd like you to do when you write, when you do your working out and you're setting out, good setting out. Highlight the information in the question, literally with the highlighter, or underline it. Write all around it. What type of information have I been given? Have I been given a mass, a volume, a concentration? Analyze your question. What is the question? Then you're going to need to write a balanced equation to know what your ratio is. Then underneath it, you're going to organize your information that you got from the question. Then we're going to have to work out the mole of the chemical that we can, so the chemical that we know something about, and in this case we're doing it with masses. So something you will know, and you can work out the moles. And then we're going to work out, using our mole ratio, the chemical that you don't know. And then once you know the number of moles of the chemical, the other chemical, then you can work out anything else about it. So the question might have asked you to find the mass of that. Okay, so pause it here and write that down. Alright, so all of that is showing if I was given the mass of something, I can work out the number of moles of it using this equation, which we'll do first. Then once I know this, I can work out the number of moles of something else with our ratio. And then once I know this, I can work out the mass of the something else using this equation. So it's a 3-step question. So we'll look at the first step. We'll look at the question and do the first step. So pause this and write down the question. I thought I'd highlighted this in green. I must have done it. Oh, I've done it on the next slide. It's all right. So I'll talk through this fairly quickly and then we'll go to the green one where you write the question down. So what masses of water is produced? So I'm highlighting the question, writing my balanced equation, putting information underneath, and then I'm turning my mass into number of moles, and then I'm going from the number of moles of this, using my ratio to the number of moles of that, and then once I've got the number of moles of the water, then I'm going to find the mass of it. So 3 steps. So we'll organize it like that. So let's write the next one down. 3 steps. Alright, so stoichiometry. So the question was, methane gas burns in oxygen to produce carbon dioxide and water. What mass of water is produced when 200 grams of methane burns completely with oxygen? So highlight the information in the question. So we've got the mass of water is the question. What mass of water is produced? Mass of water, that's the question. When you've got 200 grams of methane, that's the mass of methane. We've got some information. Burns completely in oxygen. So you've highlighted the information. And we need a balanced equation. So, always do this even if it's only quick. Sometimes you think it's a 1-to-1. You'll go, oh, it's just 1-to-1. I don't need to work it out. You know, I know this. I've got this. It's a 1-to-2. Yeah, that's when you make a mistake. So always write out the balanced equation. Sometimes you can go from it's not reacting with something else. We can look at the parts. So you can break it up and look at, if you've got the number of moles of the whole thing, you can work out the number of moles of carbon and hydrogen. But anyway, we'll do that another time. And then write the information under the equation so that it's organized. So we've got the mass of water. That's what we're trying to find out, how much of that is produced. And we've been given the mass of methane. And we don't really care about the oxygen or the carbon dioxide. The assumption is, at this point, that we've got tons of oxygen and we've got enough oxygen that it will react with all of the methane and totally turn all of the methane into water. We call the fact that we've got tons of oxygen and we're not going to run out, we call that an excess. So we don't have to worry about how much we've got. And it's going to make a certain amount of carbon dioxide, but that's not what the question's asking. So right underneath and highlight so you know the 2 things that you're connecting. And the reason that we want to know that is we want to know it's a 1-to-2. So we've got the mass. So the first step, we need to turn our mass into moles of methane. Calculate the number of moles of methane. So we know that's the equation, mass divided by molar mass. 200 grams, that's what we're given. The molar mass of carbon is 12 and hydrogen's 1. We've got 4 hydrogens, so altogether molar mass is 12 grams you need for a mole of methane. So we've got 12.5 mole of methane. Alright, so the second step, we're going from methane to water. Methane to water. So we know we've got 12.5 grams of methane. How much water are we going to make? So we need our ratio. So use the ratio So remember our ratio, what we want, what we've got, and how do those things go together? So what we want is the number of moles of water. What we've got is the number of moles of methane. How do they go together? So these have to be the same number. The 2 goes with the water, and the 1 goes with the methane. So it's 2 to 1 ratio. So this is divided on this side. We take it over the other side and multiply it. So whatever that number is, however many moles I've got here, I would have to have twice that for water. So 2 lots of that, so 25. So you've got 12 moles here, 25 moles there. Okay, so we've now got the number of moles of water. So now we want to find the mass. Make sure you've found what you've asked for. So find the mass of water. We've got the number of moles. So we're rearranging our equation to use it like this. The molar mass of water is 18. So we've got 25 moles, 25 groups. Each group is 18 grams. So altogether you're going to have 450 grams. Okay, so you notice some of you may have been pausing and writing it out. You notice that none of what I've written is green. So I would like you, when you get your questions, because we know it's a 3-step question, can you organize your page so that those 3 calculations aren't all over the place? All right, so first thing, we're going to find the number of moles of our methane. Second thing, we're going from the methane to the water with a ratio. Last thing, we're over here now, we've got the number of moles of water, so we want to find the mass of that. And I'm in the way here. Doesn't matter, you'll have the PowerPoint without me rabbiting on, so you'll be able to write that down. Alright, so hopefully I've explained that to the nth degree and it makes sense. So go from the mass of the chemical that you've got information about, or whatever information you've got, turn that into the number of moles, and then once you've got the number of moles of one thing, you can find the number of moles of anything else. So we could find, if we knew that we had 12.5 mole of methane, we can see it's a 1-to-1. You would make 12.5 grams of carbon dioxide. And if this is a 1-to-2, you would need 25 grams, 25 mole. I said grams before, didn't I? Sorry. We've got 12.5 mole of this, and we would need 12.5 mole of that. And we would need twice the amount of oxygen to totally react with it, so we'd need 25 mole of oxygen. And once you know the number of moles of any of these things, then you can work out their masses exactly the same way here. So I could relate any of those to any of the others. Alright, practicing using ratios. So it was pretty easy when it's a 1-to-2. You can just see, oh, I have to double it. That's no big deal. But it's that's why we're doing our ratio. Sometimes it's a little bit trickier. Write a mole ratio to find the number of moles of oxygen given the mole of iron. So oxygen given iron. So remember, what we want, write that on the top, and what we've got, put that on the bottom. And then these 2 numbers are what we're going to put for our ratio. Okay, so what we want, find the oxygen, we'll put that on the top, and that's 3. What we've got is iron, and that's 4, so it's a 3-to-4 ratio. So however many moles I've got of iron, I would have to multiply that by 3 on 4 to find 3/4 of it. You can kind of see that the number 3 has to go on the top, because if you're going from here that you know to here that you don't know, the number is going down. If you want to make this number of moles get smaller, you would have to multiply it by 3 on 4, not by 4 on 3. So to find 3/4 of it. Write a mole ratio to find the number of moles of oxygen given the mole of this. So what we want is still oxygen, but we're given this instead. So what we want, put on the top, what we've got put on the bottom and put the numbers that go with the appropriate things. So it'd be however much I've got of this, I would have 3 on 2 times that. Basically, that's 1.5 times that would be oxygen. So if you can see, if you're going from here to here, the number's getting bigger. I'd have to multiply it by a fraction. That's going to make this a bigger number. Okay, so with our stoichiometry, this is the stoichiometry part, going from the number of moles of one thing to the number of moles of something else, working out the amount of something else. So we've got our equations. If I had a concentration and a volume, I could work out the number of moles of something, and then I could work out the number of moles of something else in an equation. And then once I know the number of moles, I could work out the mass of that, or the number of molecules, or whatever it is. Or if I know the number of moles and the volume, I could work out the concentration of it, which we're going to do when we do titrations. Okay, oh, so much for being quick.